Continuum, tangents and normals for the ellipse. Alright, so last lesson we looked at the proof of the formulas. Okay, you can either remember the formulas or you have to derive them. Okay, I probably would personally derive them. Wouldn't try and remember every single time, because a lot of things you need to know. Okay, so the first thing we need to do is show that the line y equals mx plus or minus the square root of a squared m squared plus b squared is always the tangent to the ellipse of x squared over h squared plus y squared over b squared equals 1. So, we're going to let y equals mx plus c. Okay, with c going to equal the square root of a squared m squared plus b squared, plus minus of course. What I'm doing is just making some more life easier later on. Okay, so that means x squared, so tangent means there is one intersection point. So I'm going to substitute that y value in for the y value in the ellipse. Okay, so instead of substituting all this, square root of all that, I'm just going to substitute c, and then I'm going to deal with that later. Okay, so x squared over a squared plus mx plus c all squared over b squared is 1. Right, so we're going to remove the denominators, and we're also going to expand this. Alright, so we've got b squared x squared, m squared x squared plus 2mcx plus c squared, and that's going to be multiplied of course by a squared, and that's going to equal a squared plus b squared. Sorry, not plus, we've got times. Okay, so cross multiply, denominator moves over to the other side. Alright, so let's expand all this out. Okay, so now I'm going to factorise in like powers of x. Alright, so we've got x squared and x squared. We have the x, and then we have the constants. Alright, so we're going to factorise in terms of that. So, b squared plus a squared m squared, all out the front of x squared, plus 2a squared mcx plus a squared c squared take away b squared, and set it equal to 0. Okay, so we're thinking about this as a tangent to the ellipse. Okay, so what can you tell me about the solutions for x here? Think about it.
Solutions.
Yep. What can you tell me about the solution for this quadratic here, thinking about the tangent to the ellipse? Or how many solutions I'm expecting? One, okay, because there's only one intersection point for one tangent. Okay, so for one root, alright, so we're going back to your quadratic functions in mathematics. So for one root or two equal roots, what's the condition? Okay, so the discriminant equal to 0 will give us two equal roots, or one unique root, like one root, sorry. Alright, so solve for the discriminant. So, b squared, take away 4ac, so sum of length is third. Right, so we've got 2a squared mc, 4 squared, take away 4, lots of a, lots of c. So I'm just going to write a squared because it's already factored out. So I've got 4 times that times all that. So I'm just putting the a squared with the 4. So b squared plus a squared m squared. C squared take away b squared. Okay, so discriminant has to equal 0. So what we're leading into is we're going to have a solution for C. And we're going to show it's that. Right, that's what we're eventually leading into. Right, so we need to expand out and tidy up. So squared, so 4, a to the power of 4, m squared, c squared. Take away 4a squared. So we've got b squared, c squared. Take away b to the power of 4 plus a squared, c squared, m squared minus a squared, b squared, m squared. 0. Okay.
Don't like that. It's too messy.
Right, but it will start tidying up in a moment. Because here I've got 4a to the power of 4, m squared, c squared, 4a squared, a squared, c squared, m squared. Right, so that part and that part will cancel once I do the expansion. Right, so I'm starting to eliminate stuff, which is good. Right, so minus 4, a squared, b squared, c squared, minus 4, plus 4, a squared, b to the power of 4. No, hang on. Do we need to do that? No, I didn't actually need to do that. Because we've only got one expression for C now. Right, so if we show that C equals what I've said at the start, then we must be good. Okay, so we've already got that equation equals 0. So b squared, c squared, take away b to the power of 4, take away a squared, b squared, m squared, that all is 0 because the factor out the front, we can divide by that. Okay, so now we're solving for c squared. We can factorise the, so we can cancel the b's, okay, because they'll be all factor, we can factor out the front and then divide. Alright, so c squared must equal b squared. Take away a squared, m squared.
Going to be
Plus 6. Right, and then C is plus or minus the square root of b squared plus a squared m squared, which is what we had at the start. Okay, as required from the start. Okay, so therefore y equals mx plus or minus the square root of b squared plus a squared m squared is always the tangent to do it, because we've justified that I only have one root for all a, b's, m's. Okay, it's a bit of algebra, but we really just solved the second.
a lot of algebra.
There, bit of it. Okay, so by considering the above equation as quadratic in terms of m, then we need to show that the locus of the point of intersection of two perpendicular tangent to the ellipse will be the circle. A squared plus 4r squared equals the radius of the square root of a squared plus b squared. Alright, so from the previous page, we've got y equals mx plus or minus square root of a squared m squared plus b squared from the previous page. Right, so y take away mx all squared. It can be a squared m squared plus b squared. So move mx to the left hand side, squared both sides. Y squared take away 2mxy plus m squared x squared is a squared m squared plus b squared. So the question said consider the above equation as quadratic in terms of m. So we need to set it up as a quadratic in terms of m. Right, so we have x squared take away a squared, m squared. So we're grouping our like powers of m. Okay, this is squared. That's your power of 1. And y squared b squared is 1. So we go take away 2 xy m plus y squared take away 2 Alright, so perpendicular tangent occur when what condition must be met? Generally speaking. Go back to mathematics. So tangent must be perpendicular. What's the condition for two tangent or two?
M1,
Yep.
M2 equals.
Okay, so M1, M2 is -1. Okay, so in this quadratic, this implies that the product of roots. Okay, so we're solving for m. When we multiply the two roots together, we're going to get -1 for the two tangents to be perpendicular, and this is my polynomial's product of roots. Must equal -1 for this to work. Right, so go back to polynomials work. What were the coefficients for the product of roots for a quadratic? Go back to mathematics there.
Is that, yeah,
What were the letters?
C over A.
Good. Okay, so C over A is -1. Y squared take away B squared all over X squared take away A squared must equal -1. Okay, so y squared take away b squared is negative outside of x squared take away a squared. Right, let's go back to the question. We need to show that x squared plus y squared equals a squared plus b squared. Just about there. So if I move everything to the x squared to the left, so x squared plus y squared, and then I've got a positive a squared, and then I'll move that over to the other side and becomes positive b squared. Okay, so that is the locus of the intersection of two perpendicular tangents. Okay, so you're thinking about your ellipse. Alright, so if I put a tangent here, okay, and then I put a tangent here, alright, that's the intersection point, whatever it's going to call, just call P. Alright, so if I keep moving that around, so that this is always at a right angle, so move these 2 points around, okay, the locus is going to be the circle at centre with the radius of the square root of the, yeah. Okay, and then the actual circle itself, okay, by doing some mathematics, we can justify that it's probably drawn, okay, but circle is outside the ellipse because it's bigger than B is an A. the square root of a squared plus b squared, and we can do some maths to justify that if we need to. Hence, find the area of the least and largest rectangle that circumscribes the ellipse. Alright? So do you know what circumscribe mean?
No.
Okay, so it means that the rectangle, all four sides, has a tangent to the ellipse. Okay?
Yeah.
So it touches all four sides of the rectangle, touches the ellipse at one point. Okay? So, let's look at our diagram again. Okay, so we've got our circle, okay, with the radius square root of a squared plus b squared, the radius in there, okay, and then we also have the ellipse there. So that's b, a, etc., etc. Alright, so, thinking about this. So, the tangent must meet a right angle. Alright, so we've got four tangents, sorry. So all four corners must meet at right angles, so that means it will form a rectangle on your circumference, okay? Now remembering the locus follows this path of the circle. So the vertices of all four vertices of the rectangle must be on the circumference of that circle we just done the locus for, okay? But the tangent has to be in a way so that all four sides touch the ellipse at one point only. Okay, so from that concept, what do you think? How do you think the layout of the largest? Let's do the largest first. The largest rectangle.
Sideways, horizontal.
Okay,
Like,
this. That we say?
yeah.
That would be the smallest.
That's right. Then the other way. Sorry.
I mean, this way?
Down, yeah.
Nope.
Diagonal.
Yep.
Yeah. I get that.
What shape's that?
Which one?
What I've just drawn.
Ah, square.
Square, isn't it? Okay, the largest rectangle. Is a square. Okay, because think about it, as I rotate these points around, okay, it's going to change the point. Now this is supposed to be a tangential, circumscribe the ellipse, okay, not quite showing, but my diagram's not accurate to be able to show that. But thinking about as you move these points here around, these are all going to be right angled, they're going to get smaller. Okay, so as I move it right around, as far as I can go, where it's going to be tangent that way and that way, that's going to give it the smallest. Before I'm going to go back inside up to the maximum size, which will be at the vertices. Okay. Right, so I've got four triangles really, okay, of the same base and height. Okay, so it's considered as four triangles. Okay, so the area is going to be 4 lots of half. So for the area of the triangle. Okay, so how long is it from here to here?
Square root of a squared plus b squared.
Okay, the half base height, the half lots of the square root of a squared plus b squared times itself. Okay, which is 2 a squared plus that, and that will give you the area of the largest rectangle. Okay, so as I shift these points around, I'm then going to get again, not drawn, but these will be the corners of the circle following the locus. Right, and that'll give us the smallest rectangle. Okay, so how long is it from here to here? It's the same as here to here, isn't it?
Yeah.
So what's the distance there to there?
I forgot.
Give me the definition of your ellipse.
S. Is it S?
Hey?
Oh, S is.
Going to have the dimensions of the major and the minor axes, isn't it? Okay. The area 2A times 2B. The major axis has length 2A and the minor axis has length 2B. 4AB will give you the dimensions of the smallest rectangle to fit in that area, in that condition set. Right, a lot of algebra there, okay, but nothing particularly difficult.
How many marks would that be?
Oh,
One.
4 or 5 maybe.
Really?
This, oh, sorry, the whole question.
Just this one component.
This, you'll be looking at a couple, two, one each.
That's
Probably,
pretty good.
yeah. Will probably be a fair allocation for that.